All right, let's start. Got the recording started. It's 1 o'clock. Audio and video is up. Welcome to Statics again. We are rocking and rolling. We are at lecture 17. Just a couple quick announcements. I've got the attendance grades up to date. We've got the homeworks are rocking and rolling. So we graded homework 3.3. Homework 3.4 is due today, and then I'm going to assign homework 3.5. So we're going to keep on rocking and rolling with that. And we're going to start today with trying to take some of the tools that we've been developing, looking at moments, and seeing if we can use them to start to simplify problems a bit. And so what I mean by that is we're sort of approaching a really critical mass topic in the class, which is equivalent systems. And I'll talk a little bit about that today, but we're going to talk about a specific sort of subset of that, which is dealing with couples, which is, but we'll get to that here in a second. Let's just continue on doing a little bit of recap. So by now, you should be comfortable with the formal definition of a moment, moment being r cross f. R is your position vector. It starts at the point about which moments are taken, and it ends at any point on the line of action of f. And really what you care about from a moment in terms of its magnitude is force times moment arm. And so the force being your force vector, and the moment arm being the perpendicular distance between, or the shortest distance, I should say, between the force and the axis about which you are summing moments. Okay. Where does that lead? It leads into something that happens a lot in physical systems, and how we can simplify some of the systems that we're dealing with. And so I want to begin by introducing the definition of a couple. Okay, so if two forces have the same magnitude and they have parallel lines of action, but they point in opposite directions, they're said to form a couple. And so what I mean by that is if you have a system and you have, I don't know, some 50-pound, I'm just making the numbers up, but if you have some 50-pound force pointing this way and you have 50 pounds pointing the opposite way, and they are of equal magnitude, opposite direction, and parallel, we have a special name for that in statics and engineering mechanics, and we call that a couple generated by two forces. Now, whenever you have two forces that are separated, because those forces are not meeting at a common point, by that definition, they are going to generate a moment, okay? And they're said to generate, so said to form a couple, and anytime you have a couple, it generates moment. The moment can be computed using the same definitions that we have before, just using r cross f. The big kicker is, what is your R? Okay, so R starts on the line of action of one force, and it ends on the line of action of another, and it actually doesn't matter which one you use, you'll get the same answer. And so what I mean by that is, I'll see if I can draw it on the screen here. So let's take these two forces here. We're talking about these right there. Let's talk about these forces. There are two ways in which you could handle this. You could say, well, I'm going to sum moments about this point right here. And so if I'm summing moments about this point, then this right here, that's my R. And so R cross F will generate the moments. And think, if I take moments about that one point, this negative F force goes directly through that point. So it doesn't generate moment. So the only thing you have to consider is the R cross F of the other. So this R vector and this F vector down here. Now, similarly, you could flip that and you could say, no. Instead, my coffee's getting me. Instead, I could sum moments here. And if I'm summing moments there, then this is my R vector. So this would be R, and then I would use this vector here to compute the moments. And I'm going to get the same thing, because let's take these moments here on the screen. Those moments, or let's take these forces on the screen, not these moments. Let's take these forces on the screen. This negative F and this F are going to tend to rotate a body in a counterclockwise fashion. It doesn't matter whether or not I some moments about the tail of one force or the tail of another, I'm going to get the same answer and the same response. So it's really just a matter of preference. But in the end, you'll generate that moment. Now, what's beneficial about couples is that they allow us to begin the process of looking at simplifying systems. Okay, and here's what I mean by that. Let me stop the share here, and I want to look at that slide here in a second. So let's take a look at this example that I have here on the screen. So I have a 40-pound force acting to the right and a 40-pound force acting to the left. Okay. So if I look at this system and I think about this like I did with statics of particles. Remember, in statics of particles, we would have a point, right? And we would have, like a force here. We'd have a force here. We'd have, right here. We'd have a force here. And we'd have a whole bunch of forces all meeting through a common point. And so we could have one force, we have 6 forces, we could have 18 forces. It didn't matter. The idea behind particle statics, one of the first ones, was to try and to turn this into a particle with a single force on it that we would call the resultant. Okay? And so the idea was to simplify this system of a bunch of forces into a system with only one force. And the idea is the resultant would do the same thing that all of these forces were doing. So can we do the same thing here? Well, think about this system from a resultant perspective. If I'm looking at this system here, or this system right there, well, I've got 40 pounds to the right and I've got 40 pounds to the left. There's no forces in the x direction. So if I were to try and develop an equivalent system, the forces don't matter, because 40 to the right, 40 to the left, that doesn't matter. What does matter, however, is the moment. So I propose that this system on the left and this system on the right are equivalent systems, because both of those systems have the same net force and the same net moment, because these two forces are 8 inches apart. So 40 times 8 is 320. So I propose this system of 2 forces can be resolved into a system of 1 moment. Okay. And the idea is that if I can do that with a body that's subjected to all sorts of couples, I can simplify that to just a single force couple system. And that's kind of the idea behind what we're doing today. Now, how does that work in practice? Well, if you look at this, I've got this image here on the slide, and I've got 3 boxes that are all subjected to different force couple systems. So, for instance, the first one on the left, I've got 20 pounds that are 6 inches apart. 20 times 6 is 120, and you could see that it's rotating about the y-axis, hence why it's 120J. And it's positive because if you can kind of think of this spatially about the y-axis, it tends to want to rotate that box, what is it, counterclockwise, right? So that's the same thing that the other 2 systems are doing. We have 30 pounds times 4 inches. It's still 120. Even the one on the right, I mean, what's the difference between the one in the middle and the one on the right? We just moved the forces up. But it's still 30-pound couple separated by a moment arm of 4 inches. It's still doing the same thing to the box. So we can take these these couple systems and replace them with just a single moment vector. And so it makes the simplification of that system. It simplifies it. It makes it a little easier to deal with. What we're doing is we're sort of approaching a very important topic in statics, which is the idea of equivalent systems. See, in mechanics, we deal with systems that are subjected to a lot of forces. If you take this building has beams and columns and frames that are subjected to all sorts of forces, from dead loads and live loads and wind loads and snow and all sorts of different things. And a lot of times when we've got a system which is subjected to a bunch of forces, it's easier to resolve that into a system with a smaller, more manageable number of forces. And again, it's kind of the same thing that we did with particle statics. We had a bunch of forces all meeting at a common point. We said, let's take that bunch of forces and turn it into just a single force, and that was the resultant. Well, we're going to do the same thing here, although we've got to include the moment aspect as well, because now the forces all don't meet at a common point. And so in rigid body mechanics, this means dealing with systems that are equivalent. What do I mean by equivalent systems? I propose that two systems are equivalent if the sum of the forces in system 1 equals the forces in system 2 as well as the moments. That the sum of the moments in system 1 must equal the sum of the moments in system 2. See, in particle statics, we would never really care about that. We would just say that as long as the forces in system 1 equal the forces in system 2, they're the same, right? Because it does the same thing. Well, in rigid body mechanics, we have to consider the moments as well. So what we're doing today with this system is really sort of a special case of a more general topic that we will start next week. And so let me explain what we're going to do today. So I've got this plate here. It's like a triangular plate, and it's sort of oriented in 3 dimensions and whatnot. And, you know, it seems like there's a lot going on, but let's sort of break it down. It might be hard to see right off the bat, but if you look, there are actually 3 force couples present on this system. So I've got, let's say this right here, I've got a 16 pounds and a 16 pounds right here. Equal magnitude, opposite directions, and they're spaced 30 feet apart. That is a force couple system, okay? What about this 40 pounds? 40 pounds one way, 40 pounds another, equal opposites separated by a moment arm. What about this P vector here? P here, P there. Maybe I'll bring my blue back so you can see these. Blue here, blue here. So what I want to see is if I can take these 3 force couples and sort of resolve them into a single vector that describes the entire system. And so if I can describe the entire system with one vector, that's a lot easier than describing 6 different forces being applied all on this one system. Okay, so that's sort of the goal for what we're going to do today. Any questions before we start rocking and rolling? All right. Let me share my screen. Okay, so here we go. Okay, so here's the problem. And first thing I'll go ahead and do, maybe I'll do this in red so that it doesn't too much. Let's just go ahead and recognize the problem gave us this is 20 pounds, and this is 20 pounds. So I don't want that to be you know, I don't want you to think that's some variable. I'm giving you that at the beginning of the problem. Okay. All right. Before we get started, like doing the problem, I'm going to go ahead and write down some point coordinates. We're going to need these in order to determine some vectors later. So I figure it's probably not a bad idea to go ahead and do that now. So we're going to need point A, point B, point C, D, and E. So just to make sure everybody's awake, somebody help me out. What are the coordinates of point A? 0, 0, 20. Exactly right. All right. How about point B? And by the way, maybe before we let's do this all in inches. Okay. B is 0, 10, 0. How about C? Somebody else other than Mr. Davis. There we go. 30, 0, 0. All right. Now I want to make sure everybody else is engaged too. All right. How about point D? 15, 0, 10. And then point E. I think that might be the trickiest one, or maybe D and E are the trickier ones. 1550, exactly right. Okay. All right. I want to go through a couple of exercises here. So here's the thing. So there are three couples present in this problem. Okay. So I propose ultimately what we're going to need to do is this. Okay. I want to determine a single moment vector that describes this entire system. Okay, so to do that, what I'm going to do is this is how I'm going to write it. And I'm sure there's some mathematician out there who's going to say, oh, don't write it like that. But this is how I'm writing it. So I propose that what we're going to do is sum up the moment from the 16-pound vector, or the 16-pound force couple, I should say, the moment from the 20-pound force vector couple, or the force couple, I should use the term couple, plus the moment from the 40-pound couple. So this is ultimately what we're trying to do. Okay, so if I can determine three vectors for each of these force couples, then I can just add them together and I'm good. I'm rocking and rolling. So let's take each of these one at a time. Okay, and we're gonna do them in sort of like increasing levels of difficulty. So I'm gonna do the 16-pound one first because that's the easiest, and the 20-pound one, that one's pretty easy too. But the 40-pound one, we're gonna do the 40-pound one at the end because that's the one that I'm sure you're looking at the problem like, oh, that one looks kind of wonky, but it's not bad. Let's start off with the 16-pound force couple. Now, I'm going to do this problem two different ways. Okay, I'm going to do it two different ways. The first way that I'm going to do it is I'm going to see if I can just look at it and determine the answer. Okay, what do I mean by that? All right, let me ask you a question. So we're paying attention to this vector and this vector. What axis is this going to rotate the object about? Is it about the x-axis, the y-axis, or the z-axis? The z-axis, exactly right. So what we're going to do is we're going to say method 1 by observation. Okay. Okay, and so by observation, so we're going to say rotate about z-axis. Okay, so Mr. Adams said it rotates about the z-axis, and he's correct. Is it going to rotate counterclockwise or clockwise? Clockwise. Now, in vector notation, pop quiz, is that a positive moment or a negative moment? Yeah, there we go, negative. So the chat for some reason took a sec to catch up. Yes, that's negative. You're exactly correct. Clockwise moments are negative. Now here's the other question. Can anybody tell what a moment arm is? And what I mean by moment arm, how far is it? What is the perpendicular distance between those two forces? 30. It's 30 inches. So we take the full distance between those two forces. So I propose then that FD, and for now we're just going to do the magnitude. So FD is 16 pounds times 30 inches, and 16 times 30, that's 480, and we'll write that as inch pounds. So therefore, the moment generated by that 16-pound force couple is just going to be minus 480 times K. Why K? Because we said it was about the Z-axis. And there you go. That one's not hard, right? That's pretty easy. And yes, negative because it's clockwise. Yes. You're exactly right. Any questions? All right. Let's now if you don't like that, if you don't like the observation method, we can always do method 2. Method 2 is R cross F, to actually go through and do the cross product. Okay, so let's do that. And there's a reason why I'm doing that, because I want to check my answer, but B, one of these couples, we're kind of going to have to do that. Okay, so here's how we're going to do this cross product. What we have to do is we have to pick a point about which we're summing moments. So we're talking about this vector and this vector. Okay, and so what I propose is this. We either need to say that we're going to sum moments about that point or some moments about that point. Really, it could be any point along those vertical lines, but for ease of simplification, B or C is the easiest the easiest points to pick. And so, to be clear, it doesn't matter which one you pick, but I'll go ahead and pick this one. So, take moments about B. And so when you take moments about a point, remember the definition of R cross F. R goes from your point to the force. So this is R. And if that's R, that's F. So this is my F vector right here. So R is going to be BC. Okay? And F is going to be this vector here. Now, I'm curious, looking at this F vector, can anybody describe that F vector in vector notation by just looking at it? And so we're talking about this one right there. If you were to describe that in vector notation, what would it be? Negative 6K. Now you're right on the negative 16, but is it going with the z-axis? J. There you go. This is negative 16J. That's exactly right. Does that make sense? Because if no, that's fine. That's fine. Okay. No worries. No worries. So let me scroll down here because I kind of want to do this. I want to make sure I got space. So F is minus. I'll put my here. Let me do it like this. Minus 16 pounds times J, and then R is going to be BC. Now, the way that you determine your BC vector is you take the coordinates of C, which was 30, 0, 0, and then the coordinates of B, 0, 10, 0, and you subtract them. It's going to be 30, 10, negative 10, 0. So BC, which you can also write as R from from C to B, and that tells you how you do your subtraction. You do C minus B, is 30 inches times I minus. Now dynamics is when you're doing starting a car, like, and driving a car. So somebody's got their in their car. Now so, being in statics while you're driving, that's a contradiction. I'm joking. Okay. So this would be I could help. Okay, so this would be the R vector in this fashion. And the point I'm making is that if you want to do R cross F in this fashion, you can do I, J, K, and you can do it this way. You could say 30 minus 10, 0, because there's no term there. And this is 0 minus 16, 0, because this is 16 pounds times negative 16J, and then 30I minus 10J here for the R. And then if you evaluate this cross product, you're going to get I times, all right. So what do we get? Minus 10, minus 16, 0, and 0, minus J, and we get 30, 0, 0, 0, plus K, 30 minus 10, 0, minus 16. And so for this term, you're going to get 0. That term, you're going to get 0. And that, you're going to get K, and it's 30 times minus 16, which is minus 480 inch-pounds times K. So if you want to do it, with the R cross F method, or you want to do it by just looking at it, you get the same answer. Okay, so the R cross F or the just observation method works as long as you do it. You track your signs, track your directions, write it with the appropriate index. You can do it by observation. Does that make sense? Are there any questions on that? While you all are thinking about that, let me write that vector on the board so that we just sort of have it. I don't have to keep scrolling back and forth. So this was the moment vector for the 16-pound force couple is minus 480 K. Everybody good? Okay. Now here's my point. Let's look at this system again, and let's ask ourselves. We've done the 16-pound vector. Now we've got the 20-pound vector, or sorry, we've done the 16-pound force couple. I need to keep using that term, force couple. We've done the 16-pound force couple. Now we've got the 20-pound force couple and the 40-pound force couple. So let's talk about the 20-pound force couple. You tell me, do you think it would be easier to do the R cross F, or do you think it would be easier to just look at it and see what the answer is? See, to me, I don't know about you, but I'd use method 1 because I think you can look at it because the forces are flat. In fact, given what we did with method 1, and I'm going to scroll down a little bit so that we can see it. Given what we did with method 1, I'm going to challenge the class right now. I want you to look at this 20-pound force couple, and I want somebody to see if they tell me what vector it is by just looking at it. What is M20 equal to? Okay. We have an answer 400i. So let's digest this a bit. Okay. First off, let's ask the three questions that we asked before. So let's look at it this way. Before we jump into the answer, what axis are the 20-pound forces going to rotate this plate about? Which axis? The x-axis, the y-axis, or the z-axis? The y-axis. Okay. The y-axis. That's correct. Now, here's the kicker. We got a lot of 400s in the chat. Let me ask you a question. How far apart are these forces? They're 30 inches. They're not 20 inches apart. They're 30 inches. Because remember, this is critical. You always use the perpendicular distance. So we're saying, how far is, what is that distance? That's your moment arm right there. That's D. And D in this case is 30 inches. Okay. Now that's, so we got the 30 inches. So we know it's 600. We know it's J. Now the $64,000 question is what direction? Now think about this. Think about this spatially. Along the y-axis, it rotates positive. There you go. So it's rotating positive because it's rotating counterclockwise. So counterclockwise about the y-axis is a positive j vector, and it's 20 times 30. There we go. Now we're rocking and rolling. Okay, so let me scroll down a bit, give myself a little bit of room. So let me get my setup here. So sure. Give me 1 second. Let me write a couple things down, and I'm gonna illustrate that. I know that this could be a little strange, but okay. So 20-pound force couple. Let me write all this out, and then we'll talk about that. So rotate. All right, so FD is 20 pounds, 30 inches, which is 600 inch-pounds. And so M2O is positive 600 J. I just wanted to get all that written out, and then we're going to talk about the direction here in a second. So let me put this here. So this is positive 600J. Okay, now, Mr. Brown, you asked a question about the rotation. Okay, so let's go back to the image here. Okay, so whenever you're looking at a force couple, so you agree that the two 20-pound force vectors, and so we're talking about this one and this one, okay? So they are going in equal and opposite directions, okay? So the easiest way to think about this is, and not to reference earlier, but to think about this like your hands were on a steering wheel, okay? So imagine my hands were on a steering wheel, okay? And my hands were at 3 and 9, right? Okay, so in order to rotate the steering wheel, my hands have to go in an equal and opposite direction, right? They either have to raise up, like my right hand raises up and my left hand raises down, or vice versa, like my left hand goes up and my right hand goes down. The difference is whether or not which direction I rotate the wheel. But the axis about which the wheel rotates sort of like goes in and out of my chest, right? If here's the wheel, so let me turn my screen off for this because I want this to make sense. So here's the wheel, right? Okay, and so I'm either going to turn it this way or turn it this way. But the axis about which it rotates is going this way, right? So if here's the steering wheel, then the axis about which it rotates is like this, right? Now, when you look at at this example, look at the 20 pounds and ask yourself which axis about which it's rotating. And that 20-pound force couple that you can see, it rotates about the Y. Does that make sense? That's a great question. Again, don't hesitate to ask about this stuff. This is important stuff. Now, so I've got the 16-pound force couple vector. I've got the 20-pound force couple vector. I need the 40-pound. Now, here's the thing. The 40-pound, I got forces going all over the place. Like, there's a lot going on here. Okay, so because they're at an angle, I propose we need to use method 2. Now, in order to do this, we kind of need to pick a strategy. So here's what I'm going to do. Okay, I'm going to say that we're going to take moments here. And you don't have to. You'll see how you could do it the opposite way here in a second. I'm going to say that that's my R vector. Okay, and so my R vector is going to be dB. All right, and then my force vector is going to be this one right here. That's my force vector right there. Okay, and my force vector is going to be along BA. Okay, all right. Now, I could very easily have flipped that and said, well, instead of summing or taking moments about D, I'm going to take moments about B, and I'll show you what would happen in a second. But you know, we kind of need a strategy, so we're just going to pick one. So you can either pick D or B, either one works. So let's do some figuring here. So okay, so first thing we need is vector dB. Okay, so vector dB is going to be the coordinates of B minus the coordinates of D. You know, you do that backwards. Okay, and B was 0, 10, 0. And this is 15, 0, 10. So this is 15, that's negative 10, negative 10. And so my dB vector is going to be minus 15I plus 10J minus 10K. And first off, that's in inches. And if we scroll back up here, we can see that that was going to be my R vector. So R is that right there. So R, if we want, we can write it in that notation the way that we did the subtraction. You don't have to, but you can. So minus 15I plus 10J minus 10K. There's that. Okay. Now that's the R vector. What about the force vector? Well, the force vector is going to take a little bit of doing because we're going to need the BA vector. And you're going to see what we're doing here with the force vector. We've done this plenty of times before. So we're going to take the coordinates of A, which is 0, 0, 20. And we're going to take the coordinates of B, which is 0, 10, 0. And we're going to say 0, we're going to say minus 10, we're going to say 20. And so BA is minus 10J plus 20K. That because we need a unit vector. Because remember, how do you do a force vector in 3D? You get your distance vector, divide it by the magnitude. and then get your force vector as a result. So this is in inches. We need the magnitude of BA, which is, minus 10 squared plus 20 squared. And so when you plug and chug that, here, maybe I should put inches. That is, what is that? 22.361 inches. And so therefore, my unit vector is going to be that plus that and so that's that. I kind of just did that for us, but we've done that a number of times, so I'm hoping that I can just sort of steam through that. Is that okay? Are there any questions on this? All right. And then lastly, my force vector is going to be my force times lambda. Now, we're dealing with a 40-pound force couple, so my force is 40 pounds times this, and then when I chug that out, I get F is it ends up being minus 17.889 J plus 35.777 K. Actually, hold on. I forgot to put the units there. Oh, that got away from me. Okay. All right. Any questions? Any questions? All right. Okay. So therefore, your moment vector for that is going to be R cross F, which is going to be I, J, K, and then the R vector was what was it? It was minus 15, 10, minus 10, and then this is 0, and what is actually, maybe move this over a bit, because this is like minus 17.889, and then K minus 10, and then there's that. Okay. Now, at this point, I'm hoping that, like, at this point, that you are comfortable enough with doing cross products. So hopefully you're okay if I just tell you the answer. You're going to end up getting, when it's all said and done, 178.89 I plus 536.66 J plus 268.33 K. Okay. And it, we can go through that if you would like. If there's, I mean, I'm happy to do that. Okay, all right. So just to recap, we've got our M40 vector, and so we also have M16 and M20. So if I take M16 plus M20 plus that, that's going to give us our composite moment vector for the entire problem. And so hopefully I think you see that this really isn't, all that confusing. So if I say, summing up moment vectors, so we have M16, M20, and M40. Now M40, I'm going to write that one first because that one's the big one. All right. M20, what did we get for M20? It was positive. What was your R in M40? R was that right there. And the reason why is because it was the, because if you scroll up, R went from D to B, and then I'm using the force from B to A. That's a great question. No problem, no problem. Now M20 is 600J, so I'm going to put that here. And then 16 was minus 480K. And so if I sum up all these moments, I'm going to get M is, let's see, 178.89I. The J's, add that up, and I get 1136.66J. And then for the K's, I get minus 211.67K. And so the idea is I can take that entire system and I can represent it as just that single vector. Okay. Now, I want to go ahead and tell you a couple more steps, and we may not have time to do this today, but that's worth mentioning in the example. In the problem asks for the magnitude and direction of this moment, but that's easy, okay? So you can determine the magnitude of the moment by just taking the x term squared plus the y term squared plus the z term squared, and determine the square root. And that ends up being, when you plug and chug it, it ends up being like 1169.95 inch-pounds. And then in terms of the direction is no different than you would do in any other problem. You'd get a unit vector, which would be the vector divided by its own magnitude, which is, I'll go ahead and tell you, it ends up being like 0.153I plus 0.972J minus 0.181K. And as for direction, does anybody remember how you get the direction? Remember directional cosines? So if I take the inverse cosine of each of these numbers, that's going to give me theta x, theta y, theta z, right? And so theta x would be the inverse cosine of 0.153, which is like 81.2 degrees, and the cosine inverse of 0.972 which is 13.7 degrees, and then the inverse cosine of negative 0.181, which ends up being something like 100.4 degrees. Again, not all that difficult. I know that we're getting close to running out of time, but I do want to show you something that I think will help you with your homework. Before I do that, though, are there any quick questions that I can resolve? I know we rushed through near the end of this, but I want to make sure this is clear. Okay, I know. Like I said, I know we're pushing time. I want to show you something. So hold on. My apologies. I want to show you something real quick on your homework. This is your first homework problem. There's two problems on the homework assignment. One of them's in 2D and one of them's in 3D. I gave you hints on this problem that I kind of wanted to run by you. On this problem, what I would do, because really what you're trying to figure out on this problem is what is that distance, which is your moment arm. And so what I would do is take each of these forces and split them up into their X and Y components. And then if you decide to take your moments about, let's say, this corner, then this force is going to go right through the corner. This force is going to go right through the corner. And so you'll only have to consider two of them. Okay. And so if a force goes through a point, it generates no moment. And so once you get your moment, you can take your moment and divide it by, moment equals force times distance. So you can take your moment and divide it by F to get the distance between those two forces. Finally, I don't really have a hint on problem 2. The only thing I'll mention on problem 2 is you have something very similar to what we did in class today. But when you get your unit vector at the very end, I just wanted to kind of make a note that if one of the terms is 0, it doesn't mean that the angle is 0. It means that the cosine of the angle is 0. And so what is the inverse cosine of 0? It's 90 degrees. So just keep that in mind as you do the problem. But that was pretty much all I had. Any other quick questions before we call it? Again, I know we're pushing it on time. All right. Well, I got a homework assignment for you this weekend. I think it's a really valuable exercise, and it'll help out with what we do next week. But that's all I have. Everybody have a wonderful weekend. Stay safe, stay healthy, and we'll see you all on Monday.